Hello and welcome back. Okay, so this is the 10th video in the VGA series, and for the most part I'm tracking with the plan I started this project with. But the section at the very end, the DACs that turn the digital signal into the analog signal the VGA monitor wants, has been called into question by a couple of my commenters. Now, I've built a basic R2R ladder to give me the 3 bits red, 3 bits green, 2 bits blue that I'm currently using for all my test circuits. But in the very first video I did say I want to increase my colour range up to millions of colours. And for that I really need at least 7 bits per channel, and realistically we should round that up to 8 bits because we're being driven by an 8-bit CPU. So what I'd like to do today is have a bit of a discussion about why a few people think that maybe I'll have a problem, explore that problem, build some test circuitry, and basically see where we're actually at. Let's take a look at that. Okay, so the plan that I had at the very start of this project was to use a 8-bit R2R resistor ladder in order to convert the digital signal coming out the rest of my circuit to the analog signal the VGA needed. Here is what the basic R2R ladder would look like. We've got a chain of resistors of one value, and then they're connected to our input bits and ground via a resistor of twice that value. And if we start looking at the part suppliers, we immediately run into a problem here that while 470 ohms is a common value, 940 isn't. But as a problem, that's an easy one to get around. We can create that 940 ohm resistance by using two 470s, and now all of the resistors in our network are the same value. So we're pretty confident that we're going to be able to get any one of a wide range of values in this form. But in the introduction I did say that this as a plan has been called into question. So we need to talk about what the problem is. And to understand that, we need to look at the resistors we're going to implement this with. I started off with some 470 ohm resistors, so let's just look at the data on those parts. And there's our problem. These resistor arrays have a 5% tolerance, and that's a common tolerance for arrays of this type. Okay, so to help us talk about and understand the reality of this situation, I've made a spreadsheet. So we've got 8 columns here, which break down the value from 0 to 255 into the binary composition. So each of the columns have the powers of 2 that we're all very familiar with. But here is the voltage that each of those bits needs to contribute to the output in order to get the 0.7 volt range that the VGA is after. Let's think about what this actually means. If I look down here at a value of 127 going to 128, then we go from the lower 7 bits set to just the top bit set. So we are relying on the combined value of these 7 bits being 1 unit under the singular value of this. And of course, in binary land, that's always true. It's exactly what we'd expect. But in the analog world, it might not be. So we have a graph that is plotting the input value against the output voltage. And we see the nice straight line linear relationship that we'd like to see. But let's take into account the fact that the data sheet said our resistors might be 5% off, which more or less is going to translate to a possible 5% difference in the voltage contribution. So now we've got this little kink in the middle. But of course, the next bit down could be the exact opposite of that. So now we've got these smaller kinks down here and a large kink at this location. So the errors we're going to create are going to be progressively smaller as we go towards the least significant bit. But still, this 5% error does seem quite significant. Any non-linearity in this is going to be a potential problem for us, as it would show up as odd grading on the colours. But if we've got a consistent relationship between the incoming value and the output voltage, i.e. the one always increases with an increment of the other, then it wouldn't be too bad, and we'd like it to be as linear as possible. So let's look at what the worst case scenario would be. Let's say our 128 value actually was 5% low, and then all of our others were 5% high. Now this is terrible. We got this big downward dip here, and that would definitely throw a spanner in the works of our digital to analog converter plans. Now, of course, what I did is I went back to the parts suppliers and had a dig around. it was immediately apparent that there were quite widely available resistor arrays with a 1% error instead of a 5%. Now we still see a little dip in the middle here, but it's a lot less pronounced. And of course what we've constructed here is the absolute worst case scenario. So I kind of feel a bit better about this now. But obviously I'd like to avoid this. You can even get resistor arrays with an even lower error tolerance, but those are quite a bit more expensive and they're available in a more limited range of values. So I'd rather go with these sensibly priced 1% ones if we can. But if we can't make it work, we should talk about some potential solutions to the problem. One is to make our R2R ladder tunable. Now it should have been clear from the graphs we were just looking at that the most significant bits are the biggest problem. So I was thinking maybe I could put some blank pads in there for resistors, and then we could measure the actual output and look at putting some tweak resistors in that would just adjust the values of the most significant steps in the ladder. Now I'm pretty sure we could make this work, but it's kind of unsatisfactory. But it's always nice to know we've got an option. Another possibility is we could use an off-the-shelf R2R ladder. Now I actually showed one of these in the 7th video in the audio series. This was a 10K R2R ladder, which I temporarily used as the means to convert the volume level into an analog signal. The only problem with that is these are limited in the range of values you can get them in, and I couldn't find any that would be suitable for directly use in a VGA circuit on its own. So here's the way we could make it work. We have the off-the-shelf R2R ladder, but then we can pass that through an op-amp in a buffering configuration and then just have resistors on the outside to shift it to the level that we actually want. If we're using that many off-the-shelf components, we could consider just using an off-the-shelf digital to analog converter. Now, a quick parametric search at one of my regular suppliers showed me this one, which would do the job. But they are £5.74 each, and so it's not exactly cheap compared to some of the other options we've been looking at, and it's not really demonstrating anything about our knowledge of the hardware. So that's kind of my least favourite option. So despite the fact that some comments brought into question what we were doing, let's talk about why it might be okay. Now we did look on those graphs and we could see that 1% is actually pretty good. Even in the worst case configuration, it would have some nasty glitches on it, but it looks like we would probably get 7 bits out of it okay. Now it's almost certainly that the errors are probably going to be sat there in a bell curve. So actually getting the worst case scenario in exactly the wrong place is probably quite unlikely. I expect the errors are more closely clustered around the center. But also, from what I know of the way these kind of resistors are manufactured, it's most likely that this 1% error margin might be of a more limited range within a particular batch of manufactured resistors. And of course, if all the resistors in the resistor ladder are off by 1% in the same direction, we're probably not even going to notice the output difference. So I think the solution here is, despite the fact that I've taken those suggestions seriously, I don't think we should be hasty and throw our original plan out. I think we should try it out and confirm it one way or another. And to do that, I want to design a very small PCB that's just going to have a single channel on it, and then we can run a series of tests on that and see if the results are roughly what we were hoping for. Let's do that. Okay, so here is the DAC circuit that currently exists in the build, and this is a little bit of schematic I created in the little side window while I was doing that. But what I want to do is design an 8-bit version of this, put that onto a miniature PCB, and then we can test and see if that's actually going to achieve what we want. Okay, so we're going to want 8 data lines in, we're going to want power and ground, and we want an output. I'll add a couple of capacitors on at the same time. It always feels weird when I set these numbers in opposite orders than on the chip, but by convention in all of my builds I've got the least significant bit on the right. Right, so in addition to the data, I'm going to stick a ground on the output. I'm using a 574 latch chip here, so we need to trigger this copy line. Now the reason why I'm putting one of these in is I'm intending for one of these latch chips to have the final output, so I'd rather test it with the exact circumstances I'm going to use. Actually, I'm going to put output and a ground on one, and blank and copy on another. Let's have a look at what we need to do here. On each of the outputs we actually need 2R, but we're going to get that by putting 2 resistors in series. That way we only need the common R value for all of our resistor arrays. To get the value we actually want, we put another set in series. Now that's actually going to get us exactly 940, which is what we want to be precise. On the breadboard we didn't have a 940 we could get, so we used the 910. Right, now between each of these we need to have a 470 in series. Now I'm expecting cries of anguish that I'm doing that. I may try and route it differently. That doesn't feel terribly neat. Okay, so that's this component of the ladder. Here's our output. Our final bit of input here needs to come down to ground via a 2R resistor. And that's only R. So that's the core ladder going. Here's the other experiment I want to run, which is bringing in a MOSFET to help clamp the output down to black when we have the blanking signal. So I'm going to use some spare resistors here. So then we'll take the output and I can take that to ground via one of these resistors as well. Okay, so what I'm going to do is I'm going to make this circuit up and then try it with and without this component. That should be easy enough. All right, let's give that a quick build. I need to get rid of that. I want to sit this on a breadboard. It's always slightly annoying when things sit on a breadboard and don't have a even balance on the number of pins they use on each side of the center rail. We want this module to be an even number of squares high. Okay, that actually takes up a lot of room. See if we can make sense of this before we move it over there. Actually, when we line stuff up at 90 degrees like this, it might even be easier to have the lines the other way. Right, so the far end, that still needs to go to ground via 2 resistors. And the output is brought to ground via one of them, via the blanking signal. Let's see if we can connect these up. I think we'll do our usual ground fills on the top and bottom. Okay, well that was a very simple PCB to design. Let's make it black. Let's take a look. This is a really nice little PCB. Now, I opted to get a stencil for this and I made a terrible mistake on the order, and I know that before I even unwrap it. I neglected to specify the size of it. This is a little reminder that for small PCBs you really do need to specify a smaller size. I normally do this kind of 150 by 100 mil. Now we have learnt that not smearing extra paste in on these resistor arrays makes life a lot easier. Didn't think that through. Unlike the 1K ones I most use, these have a very clear, correct way round. Electrically it should make no difference. Those solder blobs are not perfectly aligned, so that might give us some grief. Okay, that one was a bit of a mess, but that's entirely done. Let's take a look at this. Those look exceptionally good, no bridges. Right, now I need some pin headers, so that's 8 and then 3 doubles. That's quite a nice little module. Right, so what I need to do now is clear all my soldering stuff out the way and see if I can work out a good way to test this. Okay, I'm very pleased with the way this came out. So I did make this so I could drop it into a breadboard. I think we can make some use of the bus tester board. Let's bridge power and ground before we forget. Okay, I'll use this ribbon cable to connect those 8 data lines to my bus. Let's use a shorter one. Let's get some power to the bus tester. Try a bit of blue tack on the back of these. Right, we want VCC and ground, output line, blanking and the copy line. Blanking we'll pull down, and copy, we should take it from a button over here. Right, I'm going to use the oscilloscope for this. If we triggered off the copy line, that will give us a good starting place to look. And then we can look directly at the output. I've set the switches to output onto the bus. That's going into the inputs of our DAC circuit, and then we should see that reflected in the oscilloscope trace if that is working. Let's trigger off channel 2. Okay, that actually looks promising. Right, so each time I press button 4, we're loading a new set of values from the dip switches to the inputs of the DAC. So if I set the top bit, that will give us a value of 128. As I load it, it goes up to about the halfway point. Next bit should go 3/4 of the way up. That's looking very promising. So each one of these lines should take us ever higher. If I drop the top bit, it comes back a lot. Second highest bit's value of 64, so that should be about 1/4 of the way up. That feels like it's doing the right thing. Doing it manually like this, I don't think we're actually going to answer the big questions we've got. I need to build some circuitry that's going to cycle through all the permutations. We've got 256 different inputs here. Right, so I'm going to grab a crystal. This one is 2 megahertz, closest one to hand though. Pretty much 2 megahertz. And now we want some counter chips. I'm going to go for 163s. Start off with power in the usual place. Same with ground. Now reset is active low, so we want to pull that high for both of them. Now the count enable lines, there's 2 of each. So we want to pull one of them just high. And on the first chip we'll pull the second one high, but on the second one we'll take it from the carry. So this ties these 2 4-bit counters together into an 8-bit counter. Parallel load is active low again, so pull that high to get rid of that. Got a clock line here, we'll connect them together. And that should give us a working 8-bit counter. That is the least significant bit. We no longer want to assert that data out of the switches. Okay. Now this is kind of curious. I didn't put the power back into the bus tester, but it was managing to run just off the data lines. That's the least significant bit on the higher one. Okay, they were all off by 1. Feels right now. Right, so we'll take the copy line direct from the clock, we'll take the clock itself direct from the crystal, and we should be counting 0 to 255 repeatedly on the inputs. So if this is working correctly, we would expect to see a distinct sawtooth pattern on the scope. So let's come off the top bit there. That looks promising, doesn't it? That is corner to corner, exactly what we wanted. And I'm not seeing any of the kind of discontinuity we feared we would see in that. I mean, the line's not perfectly flat, but for ripple that's pretty low. I will do one other thing. These little springs on the oscilloscope cables are designed to minimize all sources of interference. That is definitely a lot clearer. Ah, that is fantastic. I'm really pleased with that. I think I can see a very slight deviation from a straight line as it crosses that middle point, which is the location that will be most sensitive to accumulation of error. But even then, that just feels like a straight line. So I think we've proved that's going to work. Let's just have a look at that blanking signal, because we did note before that we weren't quite getting a pull to ground as quickly as we'd like. So I'm going to take that off, let's say that bit. Oh, that's a pretty sharp pull to ground, isn't it? So I think the addition of that MOSFET is going to help. I think the only thing left to do is to see if we can plug this back into the VGA circuit and make sure it works there the way we would expect it to. Now, in an ideal world, we'd have 3 of these and 24 bits of input, but we don't. We've only got 8 bits of input, but I'm sure we can work out a way to test it. Okay, this should be fairly easy to integrate and test. Got the little circuit board here. We want the copy line from as close as possible. Ground line and power in. Almost put those in the wrong way around. I'm going to tie this ground down as well. Got a blanking signal we can take from over there. And I'm going to take red, green and blue outputs all from the same DAC. And that would give us a grayscale output if it's working right. Right, let's power on and see what we get. First program I've written for testing this. That looks promising. Okay, so what this is our old friend the parrot, but I created a grayscale copy of it and now we're outputting it to all 3 channels. Of course, because we've got resistors on the monitor side, that's kind of offset our voltage divider, so I can't really create a true grayscale output by tying the 3 lines together like this without modifying the resistor values. So we can get a better idea of what's going on by taking red and blue back from ground. So now we've got green scale. So what we should be looking at here is a good 256 different levels of green, which does look like what we've got. I did code up another program to take a look at and maybe see our gradients a bit clearer. Oh, excellent. Okay, so what I've got is the 256 different levels spread across the 80 horizontal pixels in 3 different bands. So each of these bands is offset by 72, so that means we've got a little bit of an overlap, and we're not seeing any big discontinuities in here. I'm seeing a very small amount of vertical banding, but a lot of that is probably just coming from some noise in the circuitry, which we're never going to be perfect with, particularly while we've got this bridge between the PCBs and the breadboards. But the actual output from the DACs here does look like we're getting a pretty smooth result. I'm really happy with that. And I'm also very confident that if we have 3 of these, we're going to get a really good range of colors on the final output. All right, this is awesome. We've proven out that the original plan of using an R2R ladder is almost certainly going to work and give us perfectly reasonable results. Now, what I'm not going to do is try and build a 24-bit set of DACs on breadboard after this little circuit we've built on a miniature PCB. I think what I'll do now is jump straight to the output module next time I'm sat down doing PCB design. So we'll create a single board with all 3 DACs and some other support components on it, and that's going to be a nice little standalone project in its own right. Okay, Well, as always, thanks to my patrons. Your support is always appreciated. And I hope everyone found this interesting. There's a little bit of everything in this video. So I will see you again soon. Goodbye.